All right, SCH community, welcome to part 2 of our COVID conversations. I am here again with Doctors Kaufman and Bierl. Thank you, doctors, for joining us. Thank you to the SCH community for hosting this tonight. So it's been about a year since the world as we knew it shut down. I think we can probably all remember where we were those last couple of days, what our last normal day was and what we were doing. And I think we probably all thought this was going to be a short-lived break in the action. And I'll be honest, I never thought that a year later we would still be dealing with this. So in this past year, and even in the past 6 months since we last talked, we've learned a lot. We're here to discuss updates, vaccines, treatments, and answer some of your questions regarding the current and upcoming days. And incorporated into the talk are some of the questions you guys already sent to us ahead of time, but we will also be open for questions at the end. I just also want to add that in light of the last few weeks in the SCH community, I feel like this is an even more timely conversation. It's a reminder of what this past year has looked like and what we've learned and why we really all need to stick together to get through to this to the end. So Leslie, if you want to show my first slide. I'm using this Swiss cheese model to show kind of why we've been successful on campus. It's been a year where we've had our students on campus since September in some way, shape, or form, in many activities, even if it looks a little bit different. A recent publication in the Journal of the American Medical Association supports keeping our schools open when we can have mitigation techniques in place as we are. And it's been shown that there's been little to no campus transmission when we follow these rules. So the Swiss cheese model really just shows you when you have all these mitigation techniques in place, how little virus gets through. So what are some of these techniques? Masking and double masking. We know masks work. They protect us all. Double layers or double masked, definitely the best. Ventilation, use of new aeration systems, opening windows. We've built new rooms. We've put up tents for teaching and eating. We know that that helps, being outdoors as much as possible. Social distancing, words we never had heard a year ago. Using our gyms for lunch, keeping the kids far apart while they're eating, spacing out the desks. Following really strict guidelines per the Department of Health and the CDC. This regards contact tracing, quarantines, so we know that if there's an exposure or case identified, we're not seeing spread on campus. And following rules and guidelines off campus as well, regarding isolation, hand hygiene, staying home when sick, quarantining, isolations, and so on. And finally, we're going to add the vaccine to the layers. So by the end of spring break, most of our teachers will have received their second dose. When we follow the rules, when we do all these things, we know we are safe on campus. So Charlene, I am going to turn this over to you to talk about testing.
Thank you. So a lot of the terms that I'm going to use today are probably a lot more familiar to most by now, especially that we're a year into this at this point. And so when we're talking about testing for viruses, we need to remember that this is all about the amount of virus that will end up on a tube or in a sample. And so when the virus starts to replicate inside your body, you're not symptomatic until a certain amount of it takes over. And then you can develop symptoms, and sometimes you'll never just develop symptoms at all. But you need a certain amount of the virus present in order to detect it. So when we're talking about screening by testing, we're talking about when the test is done, and it could be that it's too early, in which case it's not detected yet. That doesn't mean that it won't be detected in a few days. Can you turn to the next slide, please? So now there's probably a lot more tests that we're hearing about. There's a lot of different tests on the market. We still have a lot of PCR tests. This is still the most sensitive test out there. By sensitive, I mean it can detect virus at the lowest levels when it's present in the nose. Next, in terms of the tests that are emerging, we have a lot of antigen tests that are available. And I know they're talked about in a number of different school capacities. And those are less sensitive than the PCR. So it takes more virus on board before it turns positive. And both of them can turn positive before you get symptoms. The antigen is a little bit more reliable when you actually have symptoms. And so you see these employed in a variety of different types of settings, and I'll get to that in just a moment. The last thing to convert is antibodies. Antibodies is the body's reaction after you have cleared the virus, and so it makes it to historical infection. So that's not used so much for detecting whether or not you have the disease now. Next. So here are the different testing that you'll see in the news, and you'll see employed at, say, some of your kids' colleges and a variety of settings in the area. So we have the PCR test. The pro of these is it's very high sensitivity. The con is it's not fast. Generally, it requires a large laboratory infrastructure. There are some tests that can be done on site. They tend to be very expensive and less widely available. The antigen test is where we're seeing the explosion of more rapid testing, more things available at the point of care or where the patient is being sampled. You can get a test, but it has problems with both false positives and false negatives, and so there are trade-offs there. And then the antibody test that more and more people are having access to is the test that's used to tell whether or not you have prior disease. There's a number of different variety of the tests out there. Some of them detect whether you have prior disease. They don't all detect whether you've been responding to the vaccine. And so if you have a question, say a relative is immunocompromised and you're looking to see whether or not they're mounting a response to the vaccine, you need a special type of test. And those special types of tests are available at some locations. We just brought one, we just happened to bring one up recently. And some of those tests are now starting to tell whether or not your level of antibody can be protective. But this is still not a lot that we don't know a ton about this area yet. It is evolving, and I think we will know more in the coming months. So you'll see some strategies out there, both in the news and in various settings, particularly at various colleges that your kids may be at, you'll see settings for serial testing. And so this is where college campuses are testing students twice a week, every other day, every 3 days. There's a variety of models out there. They're usually at large residential communities, and they pose a large logistical challenge, because when you're doing this, you need a whole staff to collect all those samples. Then you need to run all those tests. Then you need to figure out what to do with all the positives and the negatives and how to quarantine. And so, for example, Penn sets up dorms where they put in students that are waiting out positive results until they can be cleared to return to their daily activities. And so those tend to be logistical challenges. The reason they're doing them serial testing is because you can't, the test the day of only tells you basically that you're not shedding virus at that moment. And so by testing more frequently, they're trying to catch people before they spread it too far. You'll also see some settings where you have event-based testing. And so this is where you need a negative PCR 1 to 3 days prior to an event. And the reason that PCR is given 1 to 3 days is because it is more sensitive and it detects a lower level of virus. So if it's negative on day 1, the thought is that by day 3, you won't be making so much of it that you'll spread it. It doesn't mean you won't spread it on day 4 and day 5. It just gives you a little window where you're comfortable that you're probably not spreading it. And the antigen is usually a test for the day of, and you're not confident that you won't spread it the next day or the day after. However, all of these, we're all still coupling this with continued masking and social distancing. So it's back to the Swiss cheese model, it's an added layer of protection that it works in some settings to facilitate some activities. Thank you. And now I'll turn it over to Dr. Kaufman.
Thank you. So if you want to talk about something controversial at a dinner party, just talk about vaccines. You'll find people on both sides of the table arguing, eventually having a food fight. It will break down into something bad. And if you think about vaccine hesitancy has been around for almost 200 years. And it probably is no more no more frequent now than it was 200 years ago. In fact, there were many newspaper, people who administered vaccine, 150 years ago were drawn and quartered sometimes, so for a very long time, this problem of the controversy around vaccines has existed. And so I'm just going to give you a couple examples so that you can kind of think about your own perspective about vaccines before we actually talk about this vaccine. So I have relatives who have had an influenza vaccine, and then they say, I'm never taking that again because I took that vaccine and guess what? I got the flu. Well, might have, but it wasn't due to the vaccine because the vaccine was killed. So you didn't get it, but the fact that they got a vaccine and got the flu right afterwards says that there's not a cause and effect there. And so many people, the vaccine that they think most about is the influenza vaccine, and it doesn't work very well. You start thinking about planning what are going to be the inner workings of that vaccine about a year before you actually give it. And then as the influenza virus changes, many times it's not even close to what the vaccine was prepared for. So it's not unusual or even unexpected that the influenza vaccine isn't going to work very well. And so if people act on their experiences, they also act on what they hear on TV and read in periodicals. And but if you think about other vaccines, think about the smallpox vaccine. So when's the last time you know someone that either had smallpox or even had a vaccine? Well, you don't need a vaccine anymore because it's been eliminated in the world, except in a couple little vials, one in Russia, one at CDC, and other than that, smallpox doesn't exist, and that the reason is because of vaccines. So that vaccine was really good. Now, what about measles? Well, look at rubella measles. So about 25 years ago, the rubella was really a big concern, and particularly of my generation. My wife was very concerned when she got pregnant because when pregnant women were exposed to children who had rubella, many times they had children who had developmental abnormalities. So rubella was really a feared infection. And when the vaccine came along, it is extraordinarily effective, saves 700, well over millions of people lives every year. And because it works so well. And the only people who get rubella mainly are people who just don't take it. And they don't take it because for whatever reason, people have vaccine hesitancy. So there's a number of things about vaccines that are really important. And one is when you deliver a vaccine that is very precise with regard to the virus or the bacterium that they're going to be exposed to, well, in most cases, humans mount a really good response if you know exactly what it is that you want to make a vaccine to. Now, in front of you, you see this little tennis ball virus, and this is a coronavirus. And remember, coronavirus is named because it looks like the sun, the corona of the sun. That is, you look at the sun and you see this fireball, and then you see things coming off of it, and that's the corona of the sun. And that's why when you look at a coronavirus under a microscope, it kind of looks like the corona of the sun. That's why it's named this way. Now, in the United States and in the world, there have been about 4 or 5 coronaviruses that circulate on an annual basis, and they tend to be mild. They cause a cold-like syndrome. And then there's been a couple that have been quite severe. The first was SARS-CoV-1, which was a virus that came in 2004, and people thought it was going to be really bad. Well, it was only really bad if you got it. And if you got it, you had a high chance of dying. But because so many people got really sick early on and died, they didn't go out in public and they didn't spread it. So in fact, that pandemic disappeared pretty quickly. And then MERS was the second one. Many of you have heard that. And all of those belong to this same family of viruses. But the fundamental similarity of all of these are those little red spikes that stick out from this. And that's really important, not only in how the virus works, but also in terms of how we develop immunity to this virus. Because as humans or as mammals, as humans, when we are exposed to something that we have never been exposed to before, we tend to develop an immune reaction to it, and we'll develop antibodies, and our immune cells will remember that, that this is foreign. And if we ever see it again, then we will attack it with our antibodies and with these immune cells. So this little red spike is really the key to coronavirus vaccines, to COVID-19 vaccines. And so can I have the next slide? I'm not controlling it. So as I said, we're calling this the coronavirus, but this is the disease is called COVID-19, and the virus that causes it is a SARS-CoV-2 virus. So sometimes people will use these terms interchangeably. Particularly, they'll call this COVID-19, but this is actually the virus. Can I have the next slide? So now I'm giving you a cross section of the virus, because this is really the key thing about these vaccines. And it's going to get a little technical here for a minute, but not that technical. So you can see that that there are these little red spikes that stick out from it, and they are appropriately named spikes. And then there's a little ring around that the spikes are embedded in, and that is that membrane is an envelope that holds everything inside. And in that little envelope, there's only a couple proteins in that. Now, think of the number of genes that we have in each of our cells. We have about 25,000 genes. That would be pretty typical. Some bacteria have almost that many. So that's a large number of genes. This little virus only has about 10 genes. And it doesn't need many genes, because the way viruses work is they enter your cell, and when they get into your cell, they take over the operation of it. So imagine, there was a factory that, that made knives, and a virus went into it, and it took its mRNA, and it now told the virus not to make knives anymore, but to make can openers. Now, the factory was there, all the steel was there, everything was there. And so a virus doesn't make those things. It just tells the factory how to work. And so what viruses are really good at is telling factories how to make viruses. They have a few genes, and those genes say, make these little red spikes, make these little proteins that are in the membrane, and make more RNA. And then package them up and send them out and head them towards somebody's nose. And we'll do it again. So that's how viruses work. And that's how this particular virus works. So there's a spike, and inside of it, you see the little squiggly thing. The little squiggly thing is nucleic acid. It's like DNA, but it's not DNA. It's the DNA makes messenger RNA, which guides the assembly and making of proteins, which would be the spike. Can I have the next slide? So I'm just going to take you through the life cycle then of a virus. So you can see the upper left is our friendly SARS-CoV-2 virus. And the little red spike in the next panel over, you can see it interacts with a little protein that sticks out of that cell. The blue part is outside. The kind of the light green part is inside the cell. And that little thing that sticks up that it interacts with the red spike is called a receptor. Now, we're not going to use the word receptor anymore. We're going to call the little spike the key, and the little receptor is the lock. And so the way receptors and locks and keys work is when that virus finds inside your nose one of those little receptors, it sticks to it. And so it unlocks the door. And when it unlocks the door, the virus goes inside the cell. And when it goes inside the cell, you can see down at the bottom, it releases its RNA. It releases that little squiggly stuff. It tells the cell, let's make some virus. And it makes RNA, it makes more spike, and it assembles that little virus and then kicks it out. That's how viruses work. That's a whole course in viral biology. You probably don't need to know much more than that. Okay, so can I have the next slide? Now, during our question and answer session, anyone who has any really complex questions, I'll let you ask Charlene. So now I'm going to talk about the vaccines. And vaccines really fall into 4 categories. And so you can see our little friendly virus there at the top. And then off to the right are these little gold squiggly things. And those little gold squiggly things are the viral genes. And then down at the bottom are 5 ways that you could develop immunity to this virus. So on the far left is a live virus, but it's a virus that's been weakened. And so for many types of viruses, for example, the early rotavirus vaccine, all your children take rotavirus to keep from getting gastroenteritis. Those early rotavirus vaccines were live, but they were attenuated. And so, which meant they'd been weakened extensively so that they didn't cause disease, but they allowed you to develop immunity to it. None of our, at this point, none of our COVID vaccines are live attenuated viruses. But remember, the thing that the fundamental thing that you need in this vaccine is a spike. You need to be able to expose the cells to a spike. And so the second one over is called an inactivated virus. So if you take this virus, one of these coronaviruses, and you take it out and put it out in the street and run over it a couple times with your car, it becomes an inactivated virus. And then you can inject that inactivated virus. It's not going to make anybody sick because it's not alive. It's not viable, I should say. But it still has the little spike proteins. And it turns out that there are vaccines that have these, that are made of these inactivated viruses. Now, the third part are these, you only put in the viral spike. And so you can, through recombinant DNA technology, through gymnastics in the laboratory, you can just make the spike. You don't make anything else. You just make the spike and you put it inside of some sort of medium, gelatinous medium, and you inject that and into a muscle, and the muscle cells will see that and they'll have an immune response to it. So that's a third way. Now, the next 2 ways one is you can take the genes out of the virus and you can take them and put them inside of a cold virus. Now, this is a different cold virus. It's called an adenovirus. All of us have had adenoviral infections. They act like colds, and many of us have had many adenoviral infections. And adenovirus, for the most part, will cause colds. They're mild, they go away. But they are really good at stimulating an immune response. So if you take an adenovirus and inside, I'm going to draw you, this is the nucleic acids, this is the DNA of an adenovirus. And if you open that up and inside of it, you put a piece of COVID DNA and then close it back and then put it back inside the adenovirus and then infect people with that. Then the adenovirus, well, it doesn't replicate, it doesn't divide, but it will deliver a spike protein. And I'm going to show you a slide in a minute that shows you how that. Now, the last way is just to take the RNA out of the virus, and you don't really take it out, but you make it. You synthesize the same RNA that's in the virus, and you put that in a jelly-like substance, and we call that nanoparticles. And then that's injected into the muscle. And once inside the muscle, it will make, it will direct the muscle cells to make a spike. So you can either deliver a spike through one or other mechanisms, or you can have the cell make its own spike. Either way, you develop an immune response to it. And that's the story of vaccines. That's how they work. Now, I had some at the bottom of this slide, I had the names of the companies, and I don't see them, and it makes me worry a little bit that maybe I don't have the right version. So hold on just one second, and I'm gonna pull up my version here so that I can tell you what they are. So,
Dr. Russel.
okay. And so I'm not sure why, but anyway, the one with the vector, this was the first vaccine that was made in the world. And the vector, it wasn't made in the United States, it was made in China. So March 1st, 2020, China decided that they were going to use this approach to make a vaccine. They took the gene because they'd had the sequence of the COVID gene, and they put it inside of an adenovirus, and they started their clinical trial in March of 2020. Now, China is distributing their vaccine all over the world. At least 15 countries now are using their vaccine for COVID-19. And they didn't have the same rigor up front. They also don't have the same rules of institutional review boards and things that, they were able to find volunteers pretty readily, I guess. And so they did these trials early. And once they saw that it created immunity, then they started using it on their own population. But because of the lockdowns in China, they were actually able to control the COVID-19 so much that they didn't need the vaccines as much, and so they have been distributing it all over the world. Now, this inactivated virus, there are 3. So China also has an inactivated virus, Russia has an inactivated virus, and India has an inactivated virus. Russia also has a vector vaccine, and it's called Sputnik 5. And so this technology is actually very simple to make. Even I'm an old molecular biologist, and even I could have done this in a month probably, if you give me the sequence. So these are the types of vaccines. Now the one with viral component, that's a Novavax. So that's the vaccine that Novavax has. And then the two RNA vaccines are the Pfizer and Moderna vaccines. So those are the names and those vaccines and how they are made. Now, can I have the next slide? So for the RNA vaccines, the Moderna and the Pfizer vaccines, the nucleic acid that you see on the left side of the screen is put inside of a lipid, of a fat, and in fat and because it's unstable, it has to be kept at a very low temperature, and has been the problem with the RNA vaccines that have caused concerns and it caused logistical issues. But once it's injected into a muscle, then the genes that you see, the genetic material there, will tell the muscle cell to make a spike protein. And once it makes the spike protein, the body sees it as foreign and it makes antibodies to it. And the response to that is very strong. And so it's a two dose vaccine. So you get one dose and then another dose about a month later. Now, if a person has had COVID-19, they're supposed to wait 3 months before they actually get the vaccine. So one question that arises is, if I've had COVID-19, do I actually ever need a vaccine? And the answer to that is almost certainly yes. We know that people who have natural infections that at about 3 to 4 months, we know that the antibody levels start tapering off, and we don't know how long immunity lasts, but the concern is that by a year or so, it's probably very low. And so the advice is that if you've had coronavirus, COVID-19, you should get a vaccine. Now, it doesn't make any difference what the vaccine is, because every vaccine you get is going to do the same thing. It's going to present the body with with those little spike proteins, one way or another. You'll either make them or it'll deliver them to you. And so there was a paper that just came out this week, though, that is really interesting, that looked at the immune response in people who've not had COVID, or people who had it and were asymptomatic, or people who had it and were symptomatic. And they got a single dose of this, of the Moderna vaccine. And I'm going to tell you the response in relative units, relative antibody units. So at 2 weeks, the people who had not had COVID-19 and got a single dose, they had relatively about 900 units of antibody. The people who were both asymptomatic with COVID-19 and symptomatic with COVID-19, their antibody response was 40,000. So their antibody response was 40 times greater. So what that meant was that they remembered that they had been exposed to this before. Their body was all prepared, and it gave this really robust response. And so people who get this vaccine if they've had COVID, many times they'll have symptoms. Now, I have some experience with that. It was March 17th, a year ago, that I had COVID-19. And I told you this the last time we talked. And then last Friday, I got my Moderna dose. And I was on the couch most of the weekend from the toxic effect. It just, I didn't have high fever or anything. I just kind of felt bad. So that's what people are predicting. And now the one question that's come up is, should I get 1 dose or 2 doses? And right now the CDC says that I still should get 2 doses. And so a month from now, I'm supposed to get another one. Now, if I got the J&J vaccine, that's only a single dose. And so if I got that, of course, I would only need a single dose. So this is how the RNA vaccines work. Can I have the next slide? And this next slide simply is a simple cartoon that shows you that the adenovirus is there on the looks like the little Sputnik there on the right. And so the spike protein is inserted into the DNA of the adenovirus. And the next slide then shows you the blue sphere is a cell. And so these, what we would call recombinant adenoviruses, that is, they have adenovirus genomes and the spike gene in them. They enter the cell, and when they enter the cell, they release the messenger RNA, and they make more messenger RNA. And then that makes more spike protein, and the spike protein is then actually put on the surface of the infected cell. And when it's on the surface of the infected cell, then immune cells come along and say, this is really foreign, this is unusual, and we're going to attack, and they will actually kill that cell. So the immune cells will develop antibodies, and they will come and kill that cell. And that's how these major vaccines, this would be the J&J vaccine, and the RNA vaccines are the Moderna and the Pfizer vaccines. So that's the main way that the main vaccines we're seeing now are made and how they're used. Can I have the next slide? So all of you have heard about these variants, and these variants. There are some that are of big concern. The United Kingdom variant, it looks like that it makes more virus, and it also infects better. And probably the reason for that is the little spike protein. Once you mutate it a little bit, it sticks into that. It's as a key, that key fits into that lock better. And by having that lock and key work better, it's more infectious. Now, we don't know if it's more deadly or not, but there are a couple other variants that are really important right now. One is in Brazil, and one is in South Africa. And then there's a major variant in the East Coast and one in California. And but it looks like that, at least for the time being, that the UK variant is the predominant one that's expanding and may become the predominant variant in the country. Now, the good news is that it looks like all the vaccines that we have right now, that they work against all of these variants. And they don't work as well, but they don't have to work as well. They probably work adequately. And so for now, there's not that much concern. Now, the vaccine makers know what the sequence of these variants are. And so they're planning on adjusting their vaccines. And within any one vaccine, they can have 2 or 3 different, different DNA sequences in there to cover a wide range of variants. The thing that's being proposed now is that at some point there may be a need for a 3rd booster vaccine, and but that's not now. But that could be later on in the year, and we'll have to see kind of how all this works out. But at this point, no one knows. But there's a strategy to deal with it if these variants are able to bypass the vaccines that we currently have. We can modify the vaccines pretty easy now because using the strategy that we use to make these vaccines. Can I have the next slide? So there's concerns about the adverse reactions from people who get these vaccines. And there was a recent report that came out of Mass General where they looked at 65,000 employees. These were healthcare workers at Mass General, and they asked them to self-report. So this is a self-reported survey, and about 85% of the people reported, completed the surveys. And what they found was that that with regard to acute allergic reactions, that 1,365 employees, about 2%, with this Moderna vaccine had an acute reaction. Now that could be acute pain, it could be acute swelling, but that's not going into shock or having anaphylaxis. The percentage of people who had anaphylaxis out of 65,000 employees were 16. There were 16 employees who had anaphylaxis. Anaphylaxis means they have difficulty breathing, they have to go to the emergency room, typically. But the unusual thing about this is that of the 16 employees, 15 were female. And there's a growing evidence that women are more likely to have these adverse allergic reactions than men. And that's across many of the trials. But of these employees who had anaphylaxis, 10 of them had a prior allergy history, and 5 of them had an anaphylaxis history. So that's why after your vaccine, you have to wait there. You have to wait there 15 minutes. Now, I thought it was interesting in the paper because it said the mean time to anaphylaxis onset was 17 minutes. So I think what that means is you get people out the door just before they anaphylax. So that's a joke. But those are the data. But anyway, you have to wait for 15 minutes after you've had your vaccine. So can I have the next slide? So I'm going to briefly talk about COVID-19 treatment now. So for the most part, 80% of people who get it are going to be asymptomatic or have very mild symptoms. And in that case, just fluids and maybe a little aspirin or Motrin or something is enough. And most people don't even need to take that. 20% of the people have a more severe reaction, and 10% really are hospitalized and have had to have more intensive therapy. Now, there are some pretty interesting therapies now that have been developed. So one are called NABs. Now, NABs are not something that you eat, but NABs, if you're in the South, a NAB has a very specific connotation. It's like a cracker or something. And but these NABs are neutralizing antibodies. And so about halfway in the course of 6 months ago, a study was done thinking, let's give these antibodies, let's give antibodies from people who recovered from COVID-19. Let's clone those antibodies and give them to people who are in intensive care units. And they did that, nothing, it didn't help at all. The reason is because they already had antibodies. They were sick. They'd been, they were already 10 days out. They already had antibodies. So people said, well, maybe we should do it earlier. So there are these antibodies, and they have these really neat names like bamlanivimab. That's one of them. That's my favorite one. And the others are here on the screen. But it turns out that when people first get sick, just the first symptoms with COVID-19, and you are at high risk of disease progression, if you give an infusion of this antibody, it stops it. It pretty much stops it in its tracks. Virtually no one who was part of this trial who got this antibody went on to be intensive care units, or actually even hospitalization. So some of you will remember when President Trump got COVID-19, he was given a cocktail. This was the cocktail he was given. Okay, so he was given this cocktail early on, and it probably slowed down the course of his disease, even though it looks like he was pretty ill. And but he never really had advanced. So this is something that that people are very excited about, and particularly for people who are exposed to a COVID-19 patient, and they are at high risk of disease progression or severe illness because of these risk factors. Now, in the hospital, when people get very sick, remdesivir is an antiviral that shortens the course of the illness. But the big thing has been giving these steroids, dexamethasone. And so this has really changed the management of COVID-19 in patients who are very sick. But the good news is that there are 4 new antiviral drugs that are in late stages of development. One of you may have heard about today. It's one of Merck's antivirals, and this is very potent. It works extraordinarily well. And when people get this illness and get COVID-19 and take this antiviral drug, it pretty much stops it in its tracks. So that pretty much concludes my discussion of vaccines and treatment.
Awesome.
Now we can take questions.
Not yet.
Okay.
I have a couple more things to talk about. Thank you for that. That was fantastic. Some of the questions that we got ahead of time actually had to do with what's coming up next. So we know we've got vaccines. We know we've been this for a year. We know we've had mitigation. So talking about summer plans, talking about travel. So people are asking about summer camps. We had summer camps that were successful last summer before we knew a lot. So I would say go into summer camps looking, asking the same questions that you're asking about school. Are they going to have a lot of outside time? Are they going to require masking? Will they screen in the morning, such as, does your child have a cold, fever, whatever? What mitigation strategies are they using? Because I think summer camps are definitely going to be a viable option for kids, both day camps as well as some of the overnight camps. And camp workers are actually now in the phase to get vaccines along with teachers. So that's another layer there that will keep your kids safe. Travel, spring break is coming up. People are thinking about their summer plans from last summer that got canceled. So we're getting a lot of questions about whether or not it's safe. So the CDC is still recommending limited travel, especially to hotspots or international travel. That being said, a lot of airlines, especially going in and out of the country, are requiring testing. to get on the plane. So keep that in mind if you do decide to travel. And if you do decide to travel, think about the fact that what's keeping you safe here has to be done there. So wear your mask, limit your exposures, drive instead of fly if possible, limit the number of people that you're with. Certainly if you're vaccinated, it helps. Traveling and socializing with your vaccinated family members is going to help, and with low risk people. But again, it's what you're doing while you are traveling. If you decide to travel, that is what's important. Going on to the quarantine rules, we got a lot of questions about quarantine rules. Can you just show, I sort of summarized them, Leslie, on the slide. If not, don't worry about it. Basically, a lot depends on the situation. Basic CDC quarantine rules say that if you are a close contact and you can stay away from that initial contact, you can quarantine for 7 days and then test out with a PCR test, or you hold off for a full 14 days. If you can't separate, so I'm home with a 3-year-old and I can't separate, well, that second person has to quarantine on the other end of my being sick. So it's my 10 days plus another 7 to 14 days. Finally, contact after having had COVID or having had the vaccine, if it's been within the last 90 days, you do not have to quarantine. So there's another plug for getting your vaccine. Finally, going on with the quarantine questions, we're getting a lot of questions as to why is Philadelphia stricter with the schools than CDC is? And that's a really good question. So I did talk to them this week. And that 14-day, what they're calling a pause, is to protect the integrity of the school. We're in close contact in a school. It's not like a home where we have 4 or 5 people. We have hundreds of people. They really truly believe that at incubation of 14 days is really the better part of value for keeping them out, because you still can test positive with a secondary attack rate after 7 to 10 days. So yes, test out at 7 days and you're quarantining the population, but we are not allowed to bring people back to school until that 14 days after a contact. And again, that's because a highly populated school within the city limits, we're obligated to that. Another question I got ahead of time was about social isolation and the risk of social isolation of our kids versus the risk of infection. And I think that's a great question. It's a problem. As a pediatrician, I know I and my psychologist colleagues are seeing more depression, we're seeing more anxiety in the kids who've been home for a year with little to no school activities. But we know that this has been important. We know it decreases illnesses. We know it decreases hospitalizations and deaths. So we're just reiterating again, safe socializing is okay. Being in school is okay. But we can't ignore the issue. We need to support our kids' mental health, but we also have to keep our community health in mind. And it is really possible to do both. So as a community, we are all in this together. We know that if we follow the guidelines, we can get through this. Our school is just a microcosm of what the rest of the world is going through, and we can really see that it takes everyone to succeed. So I want to thank you guys for your cooperation and for joining us tonight. And I am going to open it to some questions. I had a couple other ones that came through and that I got ahead of time. So I'm going to go ahead and do one of you want to just mention this CDC update that came out yesterday regarding masks and gatherings? I don't know, Charlene, if that's something you want to speak.
Sure. So the CDC did start to give permission for more social contact, maskless indoors, but they're recommending that you do so in the presence of others that are also vaccinated. Now, the obvious question that comes up there is, well, our kids aren't vaccinated yet. And so how do we think about this? Hopefully our kids will get vaccinated soon. And the way I think about this guidance is the more people, if you still keep your bubbles pretty small, still try to limit the number of different people you're interacting with, the increased number of adults that are vaccinated will keep the spread down. So that's the take I had on the CDC.
Perfect, thank you. I think that actually goes right along with another question that I had about some college students being vaccinated for various reasons and whether they can be around friends without masks if they're vaccinated. So really it's the same thing. No, they really need to keep their masks on when they're in large groups of friends. Russell, we had actually sent you the report that someone had sent me today out from Newsweek that talked about reports of deaths after the vaccine. don't know if you could speak to that for a moment.
Yeah, so the report was not relatively non-specific, but it said that after COVID vaccines that 900 people have died, 450 with each of the 2 RNA vaccines. And it doesn't say over what period of time. I have to imagine that it's over the entire time that the vaccines have been given, which, is months. And so, this is, all of you have heard, most of you at least have heard this thing that there are 3 kinds of lies. There are lies, damn lies, and statistics. And this is a statistic. And so, but only when put in context, it doesn't really make sense. So how many people die every day in the United States? Okay, well, before the COVID vaccine pandemic, it was about 6,500, 6,800, depending on the season. So that's how many die every single day. Now, when you say that people died after the vaccine, remember many of these people were 80 years old. So if you then say how many 80-year-olds would die per day, and over the course of 2 to 3 months, well, it swamps that number tremendously. So it swamps the 900 number. So I would imagine that almost all of those people died of heart attacks or of any number of natural things. But so how do we know that this isn't vaccines? Well, during the course of the clinical trials, when these 40,000 people were given the vaccines, many of them had pre-existing conditions. About 45% of people who took these vaccines had pre-existing conditions. And how many of them died? Virtually none of them died. So the answer is, when you do a controlled study and you monitor it and you know the cause of death, then you see that these deaths were not associated with vaccine administration, and it's simply an artifact of statistics.
Thank you. I actually think that we've gotten to most of the questions. I did get one interesting question that asked about should we get tested before getting the vaccine in case we are asymptomatic? And I don't believe there's any recommendation for that at this point, or that would be needed.
Heather, I have one other thing then that
Sure.
I think is worth bringing up, and that's the issue of pregnant women and COVID-19.
Yes, thank you.
So, one of the issues is, should pregnant women get vaccinated? What is the risk to a fetus or to their child, with a pregnant woman getting infected? So these studies have been pretty extensively examined, and what is apparent is that pregnant women, when they get COVID-19, they are at a significantly higher risk of hospitalization and severe disease. That's if they get infection. So the risk of vaccine to pregnant women is not known. They were not included in the trials, so we don't know. But there's no reason to believe that they would be at any higher risk than anybody else. And there have now been there have been many pregnant women now who have received the COVID-19 vaccine, and there's ongoing monitoring, and there's not evidence that they're having immediate adverse events. Okay. Now the other thing is that when you sample from the placenta, the umbilical board of blood from mothers, the virus doesn't, the normal COVID-19, we know it doesn't cross into the fetus. So the fetus doesn't have much risk if the mother gets COVID-19. We think there's almost no risk to the fetus when the mother gets a vaccination. And but one of the things that I think is important, and that is there's an alert that's gone out to healthcare workers, and that is that pregnant women are less likely than non-pregnant women to show symptoms of COVID-19. And so, so Heather, that might be, something that, I don't know how widely that's known, but that's a new report that just came out recently. And so, pregnant women, when they get COVID-19, that they may not be aware of it, but it's clear that pregnant women who get COVID-19 are at much greater risk for hospitalization and severe outcomes.
Thank you.
So that's why, I mean, the people that I've advised personally, I've suggested that the risk of the vaccine is much, much lower than the risk of getting the COVID-19.
Absolutely. Absolutely. Hold on, one more question just came through here. If you get COVID between your first and second vaccine, how do we handle that? I don't know which of you would like to grab that one.
So those are very interesting cases these days that are coming up, right? And I think it obviously depends on how sick you get. It's likely going to delay your second dose. You may have to restart the series over again. The doctors are also then going to probably take a closer look for a variant or something along those lines for those types of cases. It depends on when you pop up symptomatic relative to your dose. If it's a week to 10 days afterwards, that's less of a chance that it was present when you got your shot. Whereas if it comes up the next day, then it was probably already there when you got your shot. Hopefully, the more days that it comes after you get your shot, the less disease you actually feel, and that you don't get that you're getting some protective benefit.
And I should also say, Charlene, that the CDC is recommending that people who get COVID-19 at a period after they've been vaccinated, that those viruses should be sequenced, because those could be the variants, or it could be a brand new variant that's popped up that escapes the vaccine.
I know that's the type of situation we're watching closely for.
Yes.
What do you mean by sequenced? I don't know.
So that's the way we take a very close look at the RNA of the virus, and we look at its actual molecular sequence to see whether or not it's one of these variants that you hear in the news. So that's our methodology for determining variants.
And Charlene, one question that I've had a couple people ask me is, if they get the vaccine, can they test positive?
They can't test positive by molecular. They can test.
Well, the vaccine, is it possible that the vaccine could cause them to test positive?
Not by the molecular test on your nose. Okay. You would test positive by antibodies, but only a subtype of the antibody test. But that's a good thing, because the antibody tests are looking for your immune reaction as opposed to detecting the virus itself.
Perfect. I think this is just about our time. If anybody hasn't gotten their questions answered, feel free to email me directly or via Leslie, and we can answer any other questions that way. Again, thank you, Drs. Bierl and Kaufman, for joining us. Thank you to the SCH community. Thank you, Mandy, for setting this up for us. And I hope we helped you guys out a little bit tonight. Thank you very much.
Thank you.